In this course, we have learned so far linear algebra, calculus, including ODE and PDE solvers. Now in this week, we will focus on the entire pipeline of model building and numerical simulator development for those particular models. The goal of all model building as well as the numerical simulation is prediction. We want to know what will happen before it does happen. About some physical phenomena we want to predict, such as what will be the weather tomorrow, or how much will be the economic growth of our country next year. We want to predict them. And how do I predict them? I need a model for prediction. Now, the model that we use in engineering, usually there are three types of model. The first type is that gives us a big picture, and generally they are ODE based. It's not necessarily always they will be ODE based, but generally they are ODE based. Similarly, these ODE based models which will give us big picture, if we want to improve it further, if we want to go deep into it, if we want to know detail, then sometimes we have to look at some of the components in great detail. Usually, some of the PDE based model come there. And then there are many cases where we actually don't know the governing equations of a particular phenomena. We don't know the mathematics of a particular phenomena very cleanly, or as much as we know, they are not suitable for any prediction. In those cases, our models will be based on the available data that we have. And these are the part that we are going to cover in this course later on, that based on data, how can we predict something when we do not have equations? So they are data-driven models. Now, the model building, it's a process that requires long-term learning and long-term practice. It cannot be taught in a single course in a matter of few weeks. And I don't intend to teach that part here. That is impossible to do so. However, some important idea of model building you have to take from this course, because this course is anyway at the end about numerical simulation. Without a model, the simulation has no meaning. And this model, as well as the simulation, has to predict something about some physical phenomena. Without this entire pipeline, this practice of numerical simulation is of no meaning for engineers. So let us take this example, because this example we have discussed initially, then we didn't do about it. So let us take this example once again. The problem here was that we have a payload and we want to down that payload somewhere where it is necessary. Let us say it's a disaster affected area and we are bringing down certain food packets or medical equipments there. And we are using a parachute to down the payload. We are interested to know that how much load I can put in the parachute so that when it hits the ground, its velocity will be low enough that it doesn't harm the equipment or food that is inside. And many other parameters we may also be interested to know that where we have to drop to so that it falls in a particular place. Many other parameters we may need. The simplest model, of course, of dropping certain payload comes from using Newton's law. Here we write that m, that is mass of the payload, multiplied by du dt. U is the velocity, t is the time. So this is mass into acceleration is balanced by this mg, that is the weight of the payload. We can solve this equation. This is easy because g is a constant. This is just super simple. Then we start with u at time t equal to 0 is 0. So when I am putting the payload from an aircraft, there is no downward velocity there. I know the height from which I am releasing the load. And between 0 to T0, that is that T0 is the time when the load reaches the ground, this u dt integration should be equal to the height, and it gives us the T0. Because height is known, u I have calculated from here, so this integration gives me T0. Once I know T0, I can calculate u0. This is the speed at which the payload will hit the ground. The problem of this is that here you can see that the speed will keep on increasing if we do like this. G is a constant and du dt equals g means u will keep on increasing linearly. And if the height is long enough, then T0 will be high and the speed at which the payload will hit the ground will be very high. And probably whatever it is there inside this box, it could be food or medicine, probably at high speed hitting, it may be unusable. If we use the parachute, what parachute does is that it brings a drag force into play. Now we don't know how much exactly the drag force will be. But based on our previous knowledge of fluid mechanics, we have assumed that drag force will be given by a relation like this, that is Fd is a constant multiplied by the square of the velocity. Now I include it here. You can see my basic model becomes a particular case of this improved model. Since c equals 0 brings me back to the basic model. C equals 0 essentially means that there is no drag force, which essentially means there is no parachute at all. Now if you look at this model, then one thing comes in mind, that this payload is likely to hit a terminal speed here, which means a steady speed here. In this case, the speed is increasing in time, but in this case, it looks like that as the speed increases, the drag force will increase. And as the drag force increases, it will bring down the acceleration. So at some point, the drag force will balance this mg. And once it does, there will be no further acceleration. U will remain constant. So at this point, it will reach steady state. Du dt will be 0 because acceleration is 0. And at this point, I'll have a downward speed of my payload that will be mg by c. You can clearly see that if c equals 0, this goes toward infinity. So that says that this without parachute, this will keep on increasing. There won't be any terminal speed in that case. But with parachute, it's quite likely that it will hit a terminal speed. It gives a very good idea even before we run any simulation here, that this will be the speed which probably will attain. But how long it will take to attain this? Do we attain it before the payload hits the ground, or it's not so? We don't know that. So we have to solve this actually to get this idea. This only gives us the idea of the terminal speed, but when it will achieve the time variation, we don't get it from here. This is also a model. This is the steady model. But the steady model only gives us so much, that our system will hit a terminal speed probably sometime, but we don't know when. What we are interested about, that when it will hit the ground, what will be the terminal speed, or what will be the speed as such, and the T0, the time it takes to hit the ground. For various C and M, C comes from actually the design of the parachute, and M was the payload mass. More mass we can deliver is probably better, but then if we deliver more mass, the U will be on the highest side, which we don't want. If we solve this equation now, we can get this big picture, that how much time it requires to hit the ground, what could be the speed. We get this big picture, but it will be approximate picture, but it will be the big picture, not in great detail. So let us say that we want to solve it. We can solve it analytically, But then it may not be easy. Once we solve it, then going to this integration, it may not be easy. It may be slightly difficult here, although it can be done. Other way is that we put it numerically. We can write instead of doing this integration, we can write this dh dt is minus u. We start from certain h naught, that is the initial height, and then based on the speed, the h will come down. So dh dt will be negative of the velocity. And then the second equation is the usual equation, m du dt equals mg minus cu square, where the initial time u was 0. So we have two ordinary differential equation with two initial condition, and they are solvable actually. So we have two ODEs. They are basically uncoupled, although they look like coupled, but they are not coupled. Once we solve u, then this can be fed into here and solve h. Whatever way, numerically, we can solve it very easily. You already have the solver for this, I hope, and now you can use that. So once we solve it, we will get h and u as functions of t. We have to stop the solution because the solution doesn't know that h will be greater than 0 or less than 0. So solver will keep on running, but we have to stop the solver when h hits the ground. This payload hits the ground. That means h will be very, very close to 0. At that point, we'll stop the solver and we'll check the results. So if we actually run this, and I actually ran this using our old solver that we have developed before, you remember in the predator prey model. So using that solver, I got this result. This is the case when we have no parachute, that means c equals 0. You see that the velocity here, this downward speed, that keep on increasing linearly. And it hits very high actually, 140. The payload hits the ground in 14 seconds, very quickly, slightly above 40 seconds. At that point, the speed is 140. That is understandable because we know that this du dt is g. So you can see that 140 by 14 point something, it is about the value of g. So it's understandable that the speed is increasing linearly with du dt g. So u is equal to gt, and with t is 14 point something and g is 9.8, it would be about 140 u. 140 meter per second speed is actually very high speed, and it's very difficult for my payload if it contains some sensitive medical equipment or food product. It will be probably destroyed due to that collision at this kind of speed. On the other hand, this is the height, and I started from 1 kilometer height, and then it comes down. Within 14 seconds, it hits the ground. So very quickly it hits the ground, and we can see that how the height is changing with time. Now on the top, this is my parachute. Here I have taken this g equals 9.81 and m equals 100 kg. The same value we have taken here also. But here the c is 0. I have taken c equals 1 here. This value of 1 is arbitrary because I don't know the value of c. I have just taken it 1. With this value 1, you can see that this h has become more of a linear. Why it is linear? Because this here you can see that this speed has now stabilized. So it has hit the terminal speed very quickly in about 10 seconds, and then it hits the ground at 35 seconds. And at this time, when t equals 35 seconds, we have this u is slightly above 30 meters per second. It is pretty low as compared to the without parachute case. Without parachute, it was 140, but now it is hitting about 30. So it's better that way. Time taken without parachute was 14. Now it is about 35. So we have about the velocity of payload has decreased by 1/10 of what is the case of without parachute. The time has increased almost 2.5 times. But is this enough? Well, one thing is that this terminal speed is still high. 30 meters per second is not a very low speed. And this simulation is also pretty arbitrary because we don't know the value of C. We have just arbitrarily taken C equals 1. We have to know what could be the value of C. And that may come from certain experimental result, or in absence of that, if you need an accurate model of drag force, even with the value of C, you need an accurate model of drag force. We have taken it as CU square, but that is only a tentative idea. To calculate the drag force accurately, what we need to do is that we have to bring the equations of fluid mechanics here, the geometry of parachute here, and we have to solve them along with these equations. And all these equations of fluid mechanics, they are actually mass and momentum conservation equations. They are not only PDEs, they are actually very complicated PDEs. We have to solve them. If we solve them, then our drag force will be calculated with much higher accuracy. All this estimation of time and speed, what we are getting, they will be way more accurate than what we are doing. So coming back to the original point, what we are getting by solving this problem are the big pictures, what you see here. If we want to improve the big picture, we need to bring some additional PDEs into play. Our solution will be much more complicated. We have to solving these PDEs will be way difficult. And then once we learn something from here, we want to learn more about the structure, the forces on the structure, the stresses on the structure of the parachute. And that will require once again the equations of solid mechanics, which will be again PDEs. So it will complicate the model even further. And even in all this model, when we are talking about, we did not discuss that if there is any effect of temperature, if there is any effect of humidity, if there is any effect of the base speed of wind there. If we try to bring them, then not only our models will be even more complicated, it will also bring the equation for conservation of energy here so that we can calculate the temperature. So overall, there is no limit how far I can go model-wise. We can make it even more complicated, but the main point is you can get a big picture, and this big picture is not a very bad picture from very simplistic model like this. And then as you improve it and make it more accurate, you have to bring more and more equations and your model will become more and more complex. When you will try to solve these ODEs and PDEs, you will require linear algebra. And this is where linear algebra, PDE, ODE, everything comes together. The entire numerical method course come together to help you building the simulator. Now you see that I have made some corrections here because C equals 1 was giving me about 30 meters of speed. Here I have run the same simulation with C equals 100. Once again, I don't know if this is the value. If C is 100, U comes down to be up to 3 meters per second, which is more of a reasonable value. It looks that way. And also you see that here the speed of the falling body, it hits the terminal speed almost instantaneously. So it starts from 0 and immediately it hits the terminal speed. It goes from 0 to 3 extremely quickly, and then it stays there. Of course, now the terminal speed is low, so the time the payload takes to come down is 200 seconds. It's quite long now. But one thing is clear, that most of the travel of this payload will be at constant speed. Only in initial fraction of second there will be certain acceleration, and this is what something physically happens when we drop some payload or someone jumps in a parachute. The person who is jumping in a parachute will not feel acceleration. After a fraction of a second, it will hit steady state. Now we have a model which gives us some result. We don't know how good it is. We have to be now ready to validate our model with actual test result, and if necessary, we have to modify our model. So if we have old results, or if we do not have old results, we have to do some experiment to get results, and we have to see that is it matching with all those results. So then the entire workflow will look something like this. We have the model, then we have the simulator. From simulator we get the result, but then first the result will go for validation. From the validation study, we have to improve our model. This is where we are improving the model. Then when we are happy with our model, we believe that it is giving us acceptable result, matching closely with the validation. Our results then can be used in application. We'll talk more about this in detail in this week, but this is the general workflow that you will see in actual modeling. It is, of course, in a course like this, we cannot discuss this entire pattern of workflow starting from modeling, simulation, validation, and then how the results are used in application, because this becomes a complete project that we take up in making a thesis or making papers or making presentation. This becomes a complete project starting from a physical problem and then providing meaningful input to the physical problem through model, simulation, and validation. This cannot be taken up in any one course or in this course. So rather than going into this, we are going for some simple models in this course. Some of them you have already seen. You have seen the model related to fin heat transfer. You have seen the model related to predator-prey. That is an ecological model. All these models are useful. Those who design fins, they use, even though that simplistic fin model, they are still using it. Those who work on ecology, they use predator-prey model. Even though the model we have proposed, they are simple models. There is always scope to improve the model, but all those models are useful. Even if they look simple, they are useful, and you can keep on improving on those models. So here what we are going to do, as much as we have studied, based on that certain model we have studies and certain other type of model we'll study. So in this week, primarily what I'll do is that we'll study the models based on partial differential equation. Probably one model we'll study, and then one model I'll invite you to work on it, slightly difficult model. So I'll study an easier model, and then I'll ask to extend that to a slightly difficult model in your own time. You trying a model or doing a project is not part of this course, but if you are interested, you can do that in your own time. We'll discuss about this entire pipeline of modeling, simulation, validation, but we will not do the validation itself, but we'll talk about it, how we should do validation. In upcoming week, we'll talk about regression, optimization, and neural net. They will be more in the regime of data-driven modeling. So that's all for now. Thank you and happy learning.